Hello everyone, this is Vijay and welcome to my YouTube channel. The topic that we are going to look today is problems and fundamentals of ring theory, and these problems are useful not only for CPGET entrance examination and also useful for other university entrance examinations. So before going to the today's session, subscribe to my YouTube channel and follow me in Telegram for more updates. Now let's have a look into the today's session. Now see the first problem, what is given. See the question, the associates of 3 minus I, the associates of an element 3 minus I in the ring of Gaussian integer are, the associates of an element 3 minus I in the ring of Gaussian integers are. Here we have to find the associates of an element 3 minus I. Here, see the definition of Gaussian integer. What is meant by Gaussian integer? Gaussian integer means it is a commutative ring with unity. It is a commutative ring with unity without zero divisor. It is a commutative ring with unity without zero divisor, or it is an integral domain. Or it is an integral domain. Gaussian integer means it is an integral domain. Here we have to find the associates of an element 3 minus I in the ring of Gaussian integer. Here we have four options. Option A is minus 3 plus I. Option B is minus 3i minus 1. Option C is 3i plus 1, and option D is all above. Now see here, elements of Z of I. Elements of Z of I are in the form A plus IB. Here elements of Z of I are in the form A plus IB, where A comma B belongs to Z and I square equals to minus 1. Here we know that units in the Gaussian integer Z of I are 1 minus 1 I minus I. These four elements are the units in the Gaussian ring Z of I. Here 1 minus 1 I minus I are the units in the ring of Gaussian integer. Now next see here, associates of an element A plus IB are. Associates of any element A plus IB are A plus IB into 1, A plus IB into minus 1, A plus IB into I, A plus IB into minus I. Here associates of any element, associates of any elements are obtained by multiply that element with units in Z of I. Associates of any element are obtained by multiply that element with units in Z of I. Here if A plus IB is the element, here we have to find the associates of an element A plus IB. Then the associates of A plus IB are A plus IB into 1, A plus IB into minus 1, A plus IB into I, A plus IB into minus I. Here you have to find the associates of an element 3 minus I. So multiply 3 minus I with 1 minus 1 I and minus I. Now see here, first one 3 minus I into 1, what we get? 3 minus I. Okay. Next 3 minus I into, next element is minus 1. So 3 into minus 1 minus 3 minus I into minus 1, what do we get here? Plus 1. Okay. Next one is 3 minus I into I. Okay, which is equals to 3 into I, 3I minus I into I square. Here I square value is minus 1, minus into minus plus 1. Okay. Next 3 minus I into minus I, which is equals to, what we get here? 3 into minus I minus 3I minus into minus plus I square value is minus 1. Okay. Next to minus 3I plus into minus 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 1. Here minus 3I minus 1 minus 3 plus I, 3I plus 1, 3 minus I are the associates of an element 3 minus I. Now see here, minus 3 plus I, 3I plus 1, minus 3 minus 1. Option A is minus 3 plus I, option B is minus 3I minus 1, option C is 3I plus 1. These three are the associates of an element 3 minus I. So option D, all above are the associates of an element 3 minus I in the ring of Gaussian integers. Okay, next see the second problem. In the ring Z6, addition modulo 6, multiplication modulo 6, idempotent elements are. Here what is given? Ring Z6. The elements of Z6 are 0 to 5, and it is a ring with respect to the addition modulo 6, multiplication modulo 6. Here we have to find idempotent elements of the ring Z6. Okay. Now see the definition of the idempotent elements. an element A is said to be idempotent element, an element small a is said to be idempotent element if A square is equals to A, where this element is belongs to the ring R. Okay, if A square is equals to A, then A is an idempotent element of ring R. A belongs to R, and if A square is equals to A, then A is an idempotent element of ring R. Okay, now see here, Z6 equals what we get here, 0 to 5. See in option, if I take 2, okay, 2 square equals what we get, 2 into 2, 4. So 2 is not an idempotent element. Next to take the 3, 3 square is equal what we get, 3 into 3. But what is the modulo here? 6 is the modulo. 3 3 is a 9. If you divide 9 with 6, what is the remainder here? 3. So what we get here, 3 square is equals to 3. 3 is an idempotent element of Z6. Next, what we have 4. Okay, check the 4. 4 square is equals to 4 into 4 modulo 6. 4 4s are 16 divided with 6. What we get? Remainder is 4. 4 square is equals to 4. Then 4 is also idempotent element. Next, to take the 5. 5 square is equal to what we get? 5 modulo 6. 5 5 are 25. If you divide with 6, what we get here? Remainder is 1. 5 square is equals to 1. So observe, what are the idempotent elements here? 3 square is equal to 3. 4 square is equals to 4. So 3 and 4 are the idempotent elements of the ring Z6. Okay. Next, see the third problem. Now see the third question. What is given? Which of the following are integral domain? Which of the following are integral domain? Here we have 4 options. From these 4 options, we have to find which is the integral domain. Which is the integral domain. Now see the definition of the integral domain. A commutative ring with unity without 0 divisors. A commutative ring with unity without 0 divisors is called integral domain. Here we have one of the most important result, that is every field is an integral domain. Every field is an integral domain. And next, see this one. ZP addition modulo P and multiplication modulo P is field. This is a field if P is prime. Here we have if and only if condition. If P is prime, ZP addition modulo P and multiplication modulo P is a field. Now see the option A, what is given? Z7 addition modulo 7 and multiplication modulo 7. Here 7 is a prime number. By using this result, this is a field. This is a field. Here from this result, what we observe? Every field is an integral domain. So option A, Z7 addition modulo 7 multiplication modulo 7 is an integral domain. Here Z cross Z, it is not an integral domain. It is not an integral domain. Here 2Z, it has no unity element. 2Z has no unity element, so it is also not an integral domain. Option D, what is the definition of the integral domain? Without 0 divisors. But here 0 divisors exist. It has 0 divisors. It has 0 divisors. So Z2 cross Z6 is not an integral domain. Here option A is the integral domain. Okay. Now see the problem number 5. Permutation sigma equals to 1, 2, 5, 4, 2, 3 is an element of symmetric group S5. Symmetric group S5. Then find the index of sigma in S5. Here we have one of the permutations. Sigma equals to 1, 2, 5, 4 and 2, 3 is an element of symmetric group S5. Then find the index of this permutation in the symmetric group S5. Here we have 4 options. Option A is 34, option B is 24, option C is 44 and option D is 54. Now these cycles can be written as, here 1 implies 2. So image of 1 is 2. Here 2 implies 5. 2 implies 5. 5 implies 4. Next 4 implies 1. Write 3 as it is. Okay. Next here 1, 1. 2 implies 3. Next 3 implies 2. Write 4, 5 as it is. Okay. Now write the product of these permutations. What we get? Sigma equals to, here 5 implies 5. Here 5 implies 4. So 1, 2, 3, 4. Here what we get? 4. Next 4 implies 4. Here 4 implies 1. So here what we get? 1. Next 3 implies 2. Here 2 implies 5. Okay. Here what we get? 5. Next 2 implies 3. Here 3 implies 3. Write 3 here. Here 1 implies 1. Here 1 implies 2. Okay. Now it can be written in the form of cycles. What we get, 1 implies, first I start with 1, 1 implies 2, 2 implies 3, 3 implies 5, 5 implies 4, 4 implies again 1. Here what is the order of this permutation? Order of sigma equals to number of elements in the cycles, 1, 2, 3, 4, 5. So order of sigma equals to what we get here, 5. And we have S5, given group is S5. So order of symmetric group S5 equals to 5 factorial. That means 120. Okay. To find the index of sigma in S5, what we write? Order of S5, order of S5 by order of sigma, which is equals to 120 by 5. We cancel the values. What we get here? 24. Okay. Option B is the solution of this problem. That is the index of sigma in symmetric group S5. Okay. In next video, we will discuss some more important problems of ring theory. Thank you.